to start. So again, welcome everybody for the webinar on digitalization for optimizing integrated district heating systems. We had already 2 blocks today. The first one on the policy framework, the second one on focusing on the digitalization aspects, and now the third block on hybrid energy network systems or energy integration towards the electricity and the gas sector. Yeah, my name is Ralf Schmidt. I am from AIT Austria. I am operating agent or leader of a task share, the TS3, the task share Annex on hybrid energy networks. I'm doing that webinar in cooperation with Dietrich Schmidt from Fraunhofer IEE, who is leading the TS4 on digitalization. Although we have the same last name, we are not related at all, since Schmidt is a quite common name in Austria. We have a nice program for today. First of all, I would like to introduce you, mention that the webinar is recorded, as I mentioned already, and the video file, as soon as we have it available, will be uploaded to the YouTube channel of the IEA DHC TCP. And we will have a group photo at the very end of the webinar, so please be prepared to turn on your webcam if you want. It's not necessarily, it's not a must, but would be nice to have a bit a nice group photo of seeing some known faces, but also some new faces in the webinar. Second point, to talk a bit how we do the webinar. I know we are all very used to webinars in the meantime, but still I would like to mention that you should mute your microphone. That is still happening, that people forget this, but please mute your microphone as long as you're not speaking. If you want to speak, either put it in the chat, but we have some issues with the chat, but you can also just turn on your microphone and speak. But if so, please state your name and institution before you speak. We should turn off the webcam for general webinar in order to reduce the bandwidth. If you speak, you can obviously use the webinar, and obviously also for the group photo at the very end. And we have quite a large group of people from different cultural backgrounds, so be cautious with humor and sarcasm that might not be understood everywhere. And you cannot see the face that maybe smiles at the same time if you make a stupid comment. So now, without further ado, just introduce a bit the agenda for today. We're going to talk a bit about the Annex TS3 project on hybrid energy networks, and then we have 4 technical presentations. One is on the technologies for hybridization. That's presented by Oddgeir Gudmundsen from Danfoss. Another presentation more on the design, a GIS-based automatic design of district heating networks, from Josef Jebamalai from Komsov. And the last one, or quite interesting one that is often forgotten. A lot of people talk about hydrogen, but we're going to see a presentation on the synergies or sector coupling between hydrogen and district heating. And then we're going to have, after each presentation, we have the option to ask direct questions, but at the very end, we can also talk, have a general question on hybrid energy networks to all presenters. Now, I'm going to start with the introduction into the IEA DHC Annex TS3 and hybrid energy networks. That's a project that is looking on district heating and cooling networks in an integrated energy system context. The background is that there is an increasing need for integrating the electricity, gas grids, and heating and cooling networks, since this is seen as one of the key measures for decarbonizing the energy system. Also, is very much highlighted in the recent communication by the European Commission on sector coupling and smart energy system integration, since it triggers important synergies that couldn't be realized by optimizing the sectors individually, but also by, on the other hand, we see a couple of challenges such as competition, complexity between the different energy domains. The aim of the Annex TS3 is to promote the opportunities and overcome the challenges of district heating and cooling networks when looking at these integrated energy system context. So just saying, it is not all about electrification, but it is about looking at the overall system, making the synergies, making the advantages of each sector be available to the other, and thereby making the whole system a bit better. following a holistic approach for planning and operation, but also for assessing the network's evaluation. And we're going to consider both technical aspects and more strategic aspects. We have a couple of subtasks. Don't want to go too much into the details, but we're looking on a socioeconomic perspective. We're looking on a set of tools and methodologies. We're going to highlight a couple of case studies where these networks are developed already or demonstrated, and looking at the business models and frameworks that are enabling or maybe not are hindering the implementation of a hybrid energy network. The Annex TS3 is focusing on a couple of sector coupling technologies. And these 4 technologies are the core technologies we're going to look at. Obviously, there's a couple of enabling technologies like controllers, but also like storages, for example. But I just want to highlight that this is the coupling between these 3 different networks is mainly done via either electric boilers, power to heat and cold technologies, especially heat pumps. Power to gas are increasingly important to be considered electrolysis processes. And important point here is that there are 2 ways to connect to the district heating in my point of view. One is using the hydrogen or other gas or gases that are produced based on hydrogen for burning and creating heat and electricity, for example. But the other very much forgotten thing is to use the waste heat in the electrolysis process, or that is generated during the electrolysis process in district heating networks to increase its efficiency and obviously economic performance as well. We're going to have a presentation on that at the very end. And obviously, good old CHP plants that might change their role significantly, but still have a role in the future of district heating, since they can generate high temperatures that are not easily done with the heat pumps, for example, and also have can use the fuels if you do not have other heat sources available. You can use easily CHP plants. Anyways, that's already goes quite into the details. We're going to discuss about these points during the day. Just one point, a final point, or almost final point for the TS3, since that has been asked a lot. What is a hybrid energy network? What is an integrated energy network from a district heating point of view? Since the CHP is a well-known sector coupling technology that is introduced decades ago. So the very first district heating networks are actually already hybrid energy networks, since they connect electricity, heating, and gas. Now, in order to capture this multitude of different integration schemes, we developed within the TS3 the classification approach you see on the screen. So we are differentiating on one hand between different layers of integration, and on the other hand between between a minimum and a maximum degree of integration. Don't again want to go too much into the detail here, but just saying, for example, on the technology layer, a minimum integration could be the CHP I was mentioning. That is a large-scale CHP that is just connecting the 3 different layers or networks, heating, gas, and electricity. The maximum technology integration would be going to all these 4 coupling technologies I was mentioning and combining that with operational flexibility, advanced controls, automation, and analytics. And the similar applies for the other 2 layers. You always have a minimum integration and a maximum integration. And I would just want to highlight as well that this classification differs from the one that is quite popular currently, the idea of these 4 different district heating network generations, like from the first to the second to the third to the fourth generation, that is differentiated, especially on one hand on the temperature levels that are applied in a district heating network, on the other hand also in the age or the year that it is the dominant, best available technology. But we are trying to get here a different, a more meaningful classification approach when it comes to the integration, since the temperature level doesn't necessarily say something about the integration to the electricity and gas network. This is, and yet this is still under development. Just want to highlight the TS3 project is still it's almost at the end of the first beginning of the second half of the working phase. We had a couple of workshops in the past. We have a good cooperation with eScan, since electricity and related aspects are quite important from my point of view. So we had a year ago, 1.5 years ago, a workshop with eScan representatives, and we have some interfaces and review and feedback from eScan people to our documents and developments. So I'm quite looking forward for these things. We do not have final results yet at the moment. Yesterday we had an online telco, today is a public webinar. There's still 1 year to go. We're gonna have a next meeting at the Mission Innovation Week in Austria that I actually also would like to invite you already now. It's a Mission Innovation Week. You can, if you Google it, Mission Innovation Week Austria, will find it easily. It's in Innsbruck, a nice city in the Alps. And there we're gonna hopefully have already first results to be presented. And there's a couple of results we're expecting. One that I am personally working on is an assessment of the strengths, weaknesses, opportunities, and threats of hybrid energy networks. But there's a couple of other results. Don't want to go too much into the detail. At the end, we have a final guidebook summarizing all these results I'm mentioning. Yep, that's basically it. I would like to go now. First of all, maybe I would like to see if you maybe have some questions to the IEA Annex TS3. I don't see anyone having question. If you have a question, either raise your hand. There's a small raise your hand symbol, but I don't know if that works properly. We had some issues here, or you just can speak out and ask your question directly. No question at the moment, but we're going to have the chance to discuss points at the very end. Maybe in the overall context, more questions will come. So I'm now going to switch to the next presentation. That's from Oddgeir Gudmundsen from Danfoss. Oddgeir, you have your presentations. You want to show your presentations yourself?
Yeah, I will share it now. Hopefully, let me know when you see it.
Yes, I see it.
Yeah. So
perfect. Oddgeir, the floor is yours.
Thank you. Thank you all for being here. My name is Oddgeir Gudmundsson, and I work for Danfoss, looking on different things. And one of this is the role of district energy in the future energy system. And there it's interesting to look on what is the role of district energy in the traditional hybrid energy system. Because of course the systems have been connected since the beginning of district energy. And in that sense, the traditional district energy, it's basically an important service using low quality energy. So a dumping ground for generation of power, where the power is the highest quality, and then we have the demand for heating here with a low quality demand. But this is somewhat changing now with the more renewable energy. So the future energy generation, where we have a lot of wind power and solar and all kinds of other renewable energy sources, it brings new challenges. And in Denmark, where we have a lot of wind power, then in 15th of September last year, it was the first time we had quite a lot of excess wind power generation for over 24-hour period. And this was really a lot. And it was supplying more than 130% of the demand. And for a 1 hour period, 60% more power generation than was actually needed. This brings some challenges, of course, but it's good news, and we'll for sure hear more and more of those news. If we consider what we can do to capture this excess energy, in the current situation, of course, we can export it to different countries. In the case of Denmark, then Norway, Sweden, and Germany. But when more and more renewable power comes in, then we can easily run into the problem that we cannot get rid of the excess power. And there we have some options. We can have batteries. We can have, of course, the district energy system, so power to heat. We can run individual heat pumps. We can use thermal storages in combination with the district energy or the heat pumps. We can apply digitization, so load shifting software. We can move something in so that we can delay power consumption or increase the heat consumption. We can, of course, go to power to synthetic fuels, or simply use the power directly. And all of those technologies, of course, have their different benefits and as well abilities to capture the excess energy, or excess power. And there it can be, as mentioned before, quite a lot. So 60% above the demand for 1 hour, and then it might drop down to 20% more or even less. So it's a huge amount of capacity that we need to be able to use, otherwise we simply lose it. And it has to be done cost efficiently. Now this brings the district energy to a much more interesting role for the future hybrid energy system. Because the district energy system, they can of course capture enormous amount of energy for and very fast. Can ramp up electric boilers in a matter of a minute from 0 to 100% and basically take a lot of power. Or we can run up heat pumps, which are getting more and more used in the district heating system, and then multiply the value of the power, the excess power. And if we have big systems, like for example in Copenhagen, it's a huge amount of demand combined with either large thermal storage or pit storages. There is practically no limit on how much power it can be grabbed. But there are, of course, different supply systems that we need to consider. In the core, we of course have a thermal demand of the buildings, and if we look on it in relation to power demand, then typically we have quite a lot of heat demand in the winter period, and which goes down to a very low level in the summer, while the power demand is more or less stable. So in that sense, we need to do things smart. We cannot just electrify things and do it in that way, because then we have a huge increase in the power demand, and we'll just exaggerate the challenges when it comes to renewable. We build up the capacity to supply the power demand in that way. But the thermal supply system that are in play, there's of course the individual heat pumps, or we can have heat pumps supplied with the district energy system, which has a low temperature levels, just supplying a source for the heat pump. We can have a district heating where we have a central generation and then supply sufficient temperature levels to fulfill the heating demand. If we are in locations where we have some cooling demand, then we might also have individual heat pumps simply supplying cooling to the building, and there we could dump the excess or the heat withdrawal from the building into the district heating network. If we have a high share of cooling and heating demand, so maybe 50-50, then we might run with two sets, district heating and then district cooling network. But there are, of course, other options as well, not only district energy. We can have direct power to heat, but we don't have much flexibility with that. We can have the air conditioners, there's the split units, normal ones. We could have fuel cells and then, sure, many others. But my interest is in the district energy, so I was considering to just show you the analysis on different aspects in that way, where I compare the abilities for ambient loop systems and the district heating system. But when we are considering those, then of course it needs to be planned ahead. So all communities obviously needs to do some heat planning for the future. And when doing those plannings, they should be evaluating the supply options on a range of metrics like economics, the life cycle cost. That there is a big difference between the different technologies when you take everything into account. It needs to be considered the supply security. What if things do not go as we expect today? In that sense, the flexibility comes as well, that we need to make sure that what we design for the future is flexible enough to address it if the future is not going in our direction. And then there comes other parameters like robustness. We need to have systems that are robust, so if something happens, that they can still run. Earthquake, for example, that we don't lose the systems. And we further need high reliability. And what is coming more and more into play is resilience, that we need systems that are resilient if there is a unexpected disruption. So we have a huge storm which is ruining some parts of the system. We might have terror or cyber attacks. And then the resilience is once we have the disruption and how long time it takes until we have the system up and running again. Those are all metrics that should be considered when we are planning for the future, and hybrid density system as well in that respect. Now, district density system, they are both simple and complex. And I would say they are very simple because we're basically just supplying heat to buildings or extracting heat from buildings. But they are also quite complex. It's a lot of stakeholders, and there is actually a lot of market-specific conditions. And I will present here those cases I show here. Case one, where we have an ambient loop, so we just take heat from whatever heat source, supply it to a building, and then we have a connection point to the power system as a heat pump. And that one is compared to a normal district heating, where you have the heat source, you have the connection point to the power system as a centralized heat pump, and you supply more or less the temperature level you need for the fulfilling the heating demand of the building. And it's quite interesting to look on it from an economic perspective and different markets, because if we take one source or whatever heat source at 10 degrees and look on what the situation might be in the UK versus Denmark. In the UK, we have milder climate, so less demand than in Denmark. But due to market-specific conditions, we have quite a lot of higher prices when establishing the distribution system compared to in Denmark. And this, I think, is quite a risk if you plan for a hybrid density system and you only look on your own market and you don't look for experience elsewhere, because you might come into a solution, you prioritize solutions that are, of course, good heat pumps, energy efficient, but not economically viable in the future. And I have made analysis on different temperature level sources, 10 degrees, 25 degrees, and 45 degrees, just to get a range of different options, or different sources you might have available, and they are all the same. So just to say that we have option to take a lot of, have a good connection to the power system and take a lot of power from it, excess power, but we need to rely on experience wherever that is. If I come back to those different metrics, then we can say that obviously the economics are in the centralized sources. You save quite a lot of money. You have quite a lot of security there. you can always add different energy sources like synthetic fuel plants. They can be coupled to the district heating system, as we will hear later on. We will not lose temperature level if we are able to get the right temperature level. It's quite flexible. Distribution networks, they are simple and robust. They're also very reliable, and they are district heating systems with a central source. They are quite resilient. You can easily have multiple units, multiple coupling points, compared to if you have individual solutions. Then you're relying on one coupling point, which is the power grid, and that can be a risk. Now, I also just recently heard about how Denmark is looking on maximizing the flexibility when coupling the different system, and then in the northern Jutland in Denmark, in city Aalborg, they have decided to build a very big thermal storage of about 1 million cubic meters, and that is to give them the maximum energy flexibility so that they can support whatever renewable power generation there is. They can take whatever excess, they can balance the local power plants. So if there is no renewable and they need to ramp up to the CHPs, which may go far beyond the heating demand, they can just dump it as well into the thermal storage. They can take the waste heat from industry, whatever industry it is, even if it's fluctuating wildly. And when they also have waste incineration, which they need to dump the heat into the ambient during the summer. Now they have the ability to store that as well in this thermal storage. So it's the ultimate flexibility. And this brings me to the end. If you have any questions, then feel free.
Okay, thanks a lot, Otger. Very good presentation, interesting insights. Yeah, is there any question just very spontaneously from the audience to Otger, what he was presenting? Oh, I don't see anyone raising his or her hand. Otherwise, again, just can speak directly, unmute yourself if it's not possible to raise your hand. In the meantime, maybe I would like to know, maybe not a question, but just highlight one thing that's often forgotten. What you're mentioning, the two points you're mentioning. One is that with a district heating network, you can integrate more than one sector coupling technology. That's in an individual basis quite challenging to have a heat pump, electric boiler, maybe a small CHP. That's quite so costly to do so. And the other point is a big seasonal storage that, as you mentioned, can take whatever heat source is available and just use it. I think that are two very important key points from my point of view that have an important benefit of a district heating network and an integrated district heating network towards an integrated individual building. I think that's two things you should not be forgotten in these discussions. Any other questions or comments? Nope, I don't see anything. So then thanks, Otger, again. We're going to have a discussion at the very end again. So, but then I would like to now show my screen again. This one, I guess. So, yeah.
Yeah, so I can share my screen.
I'm okay, that's good. I mean, I'm sharing my screen, but you can also do the presentation from your computer as you want.
Yeah.
So now we have Joseph Jivamalai, I hope I pronounced that correctly, from Comsoft, a software provider for district heating networks, presenting on GIS-based automated system design or design of district heating networks. So, yep, please.
Can you see my screen?
Yes.
Okay. So today I'm going to talk about a GIS-based automated design of district heating networks using ComSoft Heat. So I am Joseph Jamale. I am working as an innovation engineer in ComSoft, and also I am doing my PhD with Ghent University. So ComSoft Heat is a tool to route and dimension the network automatically. So it can estimate the cost of the network, and you can visualize the cost breakdown of different segments, such as service connections, distribution network, transport network, and heat source cost. So, and also we can do financial analysis such as cash flow analysis over the network lifetime. It can also be done using this software. So it can be used to find the feasibility of the district heating networks. So these are some of the uses of ComSoft Heat. So ComSoft Heat is used by engineering companies such as Ingenium, Rotterdam Engineering, Overmorgen, and some other companies, and network operators such as Fluence and HVC. And also there are some cities using the software such as Nijmegen, Rotterdam, and now Amsterdam, and also some universities such as KU Leuven. And let's talk about the planning methodology of ComSoft Heat. So as an input, we need a number of inputs. So first, GIS inputs, so such as street center lines of the area, and also building polygons of that particular area. And also we need a heat demand of each building. So, and then we specify the design and cost parameters of the network. So the pressure constraints and flow velocity, and the temperature levels which needs to be there in the network. So once these inputs are specified, then the software creates a network automatically. And you see as an output the network design and the bill of material with different equipment such as pipes, substations, heat interface units, and heat sources, and also the cost of the network. You can also visualize the cash flow analysis, cash in and cash out over the network lifetime. And also you can optimize the design after the software created the automated design. You can finally man tune. So first you have the data collection, and then you prepare your data and you specify your technical and cost parameters, and the software designs a network, and you can inspect those results, and you can manually fine tune some of the parameters, and then with a click of the button you can create and compare different multiple scenarios. So then now I want to present two different cases. So one in Glasgow. So this case, so it's in the Glasgow city center. So we have a Glasgow city center, and we are going to extract a heat from a river with heat pumps. So more heat pumps can be used to extract heat from the river and feed the city center of Glasgow with energy for heating of buildings. So we have 4 heat pumps at 4 locations along the bank of the river. And then we need the inputs. So we need GIS inputs. So for this case, we used OpenStreetMap data. So for the street center lines and also the building polygons. And then we need heat demand data. So for the heat demand data, we can use gas consumption of the buildings. But in this case, we used HotMaps, which is an EU Horizon 2020 project. So the HotMaps website has the data for heat demand density and gross floor area density for the whole Europe. So we can download this data and we can estimate heat demand of the area using this publicly available data. So we used HotMaps to estimate the heat demand data. And then once you have specified the distribution network, so you can specify the design parameters. So we specified steel pipes with 16 bar pressure, and the supply and return temperatures 80-50, and 4 heat pumps supply heat to 4 different clusters. So as you can see, 4 different clusters is supplying heat from the heat pumps, and the total public trench length is 57 kilometers. So the total network linear heat density is 2 megawatt-hour per meter. So from the software, you can also see the different lengths of different pipe diameters. So DN25, how much length is needed for this project, and DN200, DN150. So these can be easily seen as an output. So then you can easily modify the network design. So initially we made the area of this particular location, and we just extended the area here in the north, and we looked into what are the implications of extending the area. Does it have any cost or financial benefit we get out of extending those areas? So then once we have this, then I'll also explain some of the deployment cost assumptions we made for this study. So we initially used different cost data for different pipe diameters, but then it was changed to constant cost, which is 2,000 pounds per meter for all the pipe diameters. So it is from expert advice from one of the project partner, because the trenching cost almost dominates the deployment cost. And also we have heat source cost and intermediate pump cost, because there is an elevation in the city center in the Glasgow. So we need to consider cost for intermediate pump cost also. And we also assumed heat delivery unit cost for different breakdown from 1 kilowatt to 50 kilowatt. And then we have different cost assumptions for different categories of heat interface units. So once we have all these costs, so we assumed 100% uptake. So which means all the buildings in that area will be connected to the district heating network. So as a result, we got an estimation of 252 million pounds for total cost of the project, which includes 34% for energy center, 17% for service connections, and 6% for demand, and 43% is for distribution network. So also what we did is we also looked into different financial parameters. So we used two different cost of heat production. So the first one is 33 pounds per megawatt hour, and the second one is 15 pounds per megawatt hour cost of heat production. So for each cases, we changed the heat sales price. So heat sales price is differed from 6 pence per kilowatt hour until 12 pence per kilowatt hour. So in the first case, for the cost of heat production, we have 33 pound per megawatt hour, and we changed the heat sales price from 6 pence to 12 pence. So you can see the IRR was negative at the start, and at 12 pence we have 3% IRR. So you see you have all negative NPVs because the discount rate was assumed 4%. So it was not beneficial. So we don't have much business case for this with 33 pounds. So we can change with 15 pound for cost of heat production if you get cheaper electricity for the heat pumps. Then we can see if you change from 6 pence to 12 pence, the IRR is, we have positive IRR around 4.4%, but still we don't have a high IRR to support very positive business case. So we need government subsidies or carbon tax to have this project realizable. But you can see how you can compare different scenarios easily with different NPV and IRR and payback time for different parameters. So this is one of the case study. And then the other case study we did was it's using multiple sources. It's an area in Kortrijk. So in this case study, you have like 6 sources and 2,300 buildings. So the building inputs we used for this project is around, we use the gas consumption data. So we map street level gas consumption data to the building level using building area ratio. And we categorized buildings using residential, commercial, and industrial. And we used load factors to estimate peak demand. So if you look at the heat source, we have a waste incinerator at the north, so which is 2 kilometers from the network. And we have 3 heat pumps in the city center, and we have a gas boiler and CHP. So we have like 6 sources and 2,400 buildings. So we assume the heat source attributes for waste incineration, heat pumps, CHP, and gas boiler. We assume the investment cost, energy production cost, and CO2 release for each of the different sources. So once we have all the heat source attributes, so we have to give the technical parameters. So in this case, we designed 2-layer network. So what do I mean by 2-layer network? So the one is transport network, so which provides transports heat from source to all the substations, and distribution network, which further distributes from the substation to each and individual buildings. So in the transport network, so the temperature level was assumed 80-50, and in the distribution network, the temperature levels are set as 70-40. So, and then the network is sized, and then the cost is estimated. So in this case, we have a supply is greater than demand. So what do I mean by that? So we have more number of sources than necessary. So we can actually select the source to meet the demand. So in order to select the source, we have like number of possible options how the source can be selected. So we can use the investment cost as a source selection criteria, or energy production cost, or CO2 cost, or combination of anything. So we can also have the combination of all of these costs to select the sources. So out of the 6 sources, based on these different scenarios, we can choose the sources. So I present the different scenarios here in this graph. So we did the scenarios for only investment cost, for energy production cost, for carbon cost, and the combination of investment and energy production cost, combination of energy production and carbon cost, investment and carbon and the total cost, which is investment, energy production, and carbon cost. As you see here in the carbon cost scenario, the investment cost is quite high because the investment cost for heat pumps are higher. So if you see the investment cost case, so in the investment cost case, you have a lower investment case. So if you see the total, which is the investment, energy production, and carbon cost, you have somewhere in the middle between the carbon scenario and then the investment scenario. At the same time, if you look at the energy production cost, it's also costlier for the carbon scenario because heat pumps has higher energy production cost. But then the CO2 cost is much lesser because heat pumps doesn't have much carbon emissions. So in the CO2 cost, the carbon emission scenario have much lesser CO2 cost, but then investment cost which have higher CO2 cost, and these investment, energy production, and carbon cost scenario at the end, which has somewhere in between the carbon scenario and the investment cost scenario. And then if you also look at the CO2 emissions for these different scenarios, so the investment cost and energy production cost, these have high CO2 emissions, and then the carbon scenario, which has very less CO2 emissions at the expense of higher investment and energy production cost. Also, you can see the CO2 saved based on the reference CO2 emissions. So the carbon cost scenario have much higher CO2 emissions. So using this scenario, we can easily see what is the optimization, what is the source we need to select out of the given sources. So then here I am showing this case with investment, energy production, and the carbon cost, both combined. So 3 sources are selected out of 6. So these sources are one heat pump and a waste incinerator and a CHP plant. So here we have CHP, which is connected to electricity grid, and heat pumps, which are also linked with electricity networks. And we can have storage, which is also easily integrated in this model. So these kind of integrated approach of different networks are necessary to increase the renewable energy share and eventually move towards the sustainable energy solutions. So that's all. So I'm happy to take questions. Thank you.
Okay, thank you, Firoza. Sorry, thank you, Firoza, for your presentation. Again, any question from the audience, from the group, to Joseph directly for the methodology and the tool he was presenting? I would actually have a question, 2 questions. One was on the different heat sources you were explaining. Heat pump, CHP, waste incinerator, and I think it was a boiler also you had as an optional heat source. Is there how you optimize, how you calculate the benefits, or how you like the different costs you were calculating? Is there, because I mean the operation of the CHP and the heat pump, that is the core of a hybrid energy network. So one of the cores is kind of dependent on each other a bit, and it's basically also depending on the electricity prices and especially on the fluctuation. So are you considering fluctuating electricity prices, or you have a flat rate for electricity?
We are having flat rate for the electricity, but we can also consider the inflation rate, which is an input parameter which can provide. So based on the input parameter, we are choosing the different sources. But for the selection of sources, for example, for the investment cost, we only look at the investment cost, which is calculated based on the input provided. And also for the carbon cost, everything is estimated based on the network lifetime. So we get an overall network lifetime. So based on the network lifetime, we calculate what are the costs for each from each source. What is the cost we get for the overall network lifetime, and based on that, we select the sources based on these inputs.
Okay. And I see there's another question from Clemens Felsmann.
Yes, thank you. Thank you for presentation. So my question is about the simulation that is in behind. So to calculate heat losses, to calculate the energy demand of the pumping. So what kind of simulation is in behind?
So it's so initially we route based on the cheapest route. So once we have routing, we dimension the pipes. So based on the pressure constraints we have, so we can have 3 design constraints. You can either specify flow velocity or the pressure constraint. So 1 to 6 bar or 10 bar or 16 bar. And also we calculate the pressure losses along the pipes when it's routed. So based on that, if it respects the pressure constraints, then we dimension the pipes. And also heat losses, we calculate based on normal heat loss calculation. So it's we only do it for the peak. We don't consider for other times. So we only do that for the peak. And for the heat loss calculations, we have to have a profile. So load profile has to be updated. So based on the load profile, we calculate heat losses for different time frames, and we provide the heat losses for over the year.
Okay, so thank you.
Okay, any other questions to yourself?
I would have one. I'm sorry, but it doesn't work to raise the hand or
Okay, no problem.
write a message in the chat. You have just explained that you calculate this for different time frames. So do you really have a simulation, a dynamic simulation with a time resolution? What is the step size here? Or are these single calculations for different load conditions?
So it's the design itself is for only for the peak, but only for the heat losses we use load profiles just to give the yearly total losses. But this is not doing any dynamic simulations. It's only do it for the all the design and calculations and network pipe estimations, but that everything is only for the peak demand. So we design for the peak demand, and only for the heat losses we use the profiles to calculate the heat losses over the year.
And a second question, thank you for this answer. And the second question, how detailed is your mathematical representation of the grid you finally calculate? Is it really that you can define each single pipe, or?
So this method for the multiple source method, so we need to do several iterations to come up with the optimal solutions. So it just assignments and the routing. So we have the concept software, they have routing algorithms. So it calculates different routes. You can specify cost for each streets. What is the cost for, maybe based on the concrete or based on the other network grids concentration. You can specify cost for each and every street cost. So based on that, they route, and then here based on the cheapest routing, we assign for each substations to the sources, and we iterate based on different orders of substations, and then we come up with the optimal solution based on different iterations. So for this particular design, it was around 24 different iterations to come up with the optimal solution.
And how detailed is the grid then described?
So the grid you can see until from the transport network, and you can see the distribution network, and you can even see the pipe connection to the end of the building, and you can see the pipe dimensions, and you can see also every parameters of that pipe associated with that pipe.
Thank you. Very impressive.
Thank you. There was one other question, but that is gone already. So whoever, I saw just one hand, I don't remember who was it. But is there any other questions at the moment? That seems not to be the case. So thanks again for your presentation. And we're gonna go now to the last presentation of today. Hans, you would like to present it from your screen, or should I present it on my screen?
Then I will share my screen.
Okay, perfect. So then now we have a presentation sector coupling, what I was mentioning, between hydrogen and district heating. We're looking forward for this often overseen aspect. We actually see the presenter view now,
Okay.
not the full presentation.
So now it should work.
No, I still see the presenter mode.
doesn't really seem to work.
No. So should I present then for my?
Yes, please.
That's maybe a bit, because I switched off the presenter mode and then it's working. But I'm gonna do that now. No. Is it working? Can you see my screen?
Yes, perfect.
It works fine.
Wonderful. So then, Hans, floor is yours.
Yes, thank you. So my name is Hans Böhm. I'm working as a researcher and PhD student at the Energy Institute at the Johannes Kepler University in Linz. And I'm mainly dealing with techno-economic analysis, primarily for power-to-gas and hydrogen applications. And now I would like to talk about some selected aspects of sector coupling between hydrogen and district heating. Next slide, please. So when we are looking at this visionary picture of a future hydrogen-based energy system, one can already imagine the manifold applications for hydrogen and power-to-gas, reaching from industrial processes over residential usage to transport and mobility applications. So sector coupling and sector integration is really an important aspect to increase energy efficiency, especially in terms of waste heat utilization. So let's have a look at the technical opportunities we have. Next slide, please. When looking at electrolysis as the main technology for producing green hydrogen from renewable electricity, we can basically categorize these in low temperature and high temperature electrolysis. Low temperature electrolysis is usually supplied with liquid water and operated as an exothermal process, and therefore requires external cooling. On the other hand, high temperature electrolysis can also be operated with steam instead of liquid water and below the thermoneutral voltage. And this means that it allows to partly provide the energy demand from external heat sources, and so reducing the electric energy demand and therefore increasing the electric efficiency of the electrolysis process. Next slide, please. So looking at the state-of-the-art technology options, one can already see that PEM and alkaline electrolysis as low temperature applications mainly encourage thermal integration in especially close applications or wherever temperature level is of secondary importance due to temperature levels from 50 to 90 degrees Celsius. On the other hand, for heat-intense industry, they would rather use high temperature electrolysis to utilize their waste heat to increase the efficiency of the hydrogen production. However, this could lead to increased heat demands in future district heating if today's suppliers, such as steelworks, tend to use their waste heat internally instead of supplying district heating grids. However, when talking about power-to-gas or power-to-X processes, also the downstream synthesis processes, such as methanation, for example, should be taken into account for waste heat utilization, since they often provide heat at elevated temperatures. Next slide, please. When it comes to energetic utilization of hydrogen, fuel cells are the main conversion technologies. So looking at current technology options as listed here in this table, it can clearly be seen that there are technologies available that on the one hand already provide heat at elevated temperatures and can be used in CHP applications, and on the other hand are already available at multi-megawatt scale. So next slide, please. So how are these technologies supposed to be used in terms of sector coupling in future energy systems? If we take Austria as an exemplary use case, we can already say that national renewable electricity potentials will not cover the Austrian consumption, neither profile nor balance related. So the trade-off between electricity supply and demand requires short-term and long-term storage options, and therefore seasonal storage in the forms of hydrogen or power to gas and its derivatives will be essential. However, this also means that today's gas infrastructure will still be required in the future or in future sustainable energy systems to supply renewable gas CHPs as backup capacities, but also industrial applications using hydrogen or SNG as energy carrier or feedstock materials, and also other customers such as transport and mobility applications. Next slide, please. So let me give a concrete example for the integration of hydrogen and district heating. Let's start with a conventional CHP plant connected to existing gas infrastructure, district heating and power grid. Next slide, please. So now assume that electrolyzers will play a significant role in future energy systems using renewable electricity to generate hydrogen for direct utilization or partly feeding into gas grids. So in this context, it has to be kept in mind that the two processes, CHP and electrolysis, are usually operated at different times, depending on the electricity and probably heat supply and demand. Next slide, please. So this can be taken a step further by taking downstream synthesis processes into account, like methanation, which provide opportunities for carbon capture and utilization, as well as direct substitution of fossils, and thus enable carbon cycle economies. Next slide, please. So now we come to the heating part. If we take this system as a whole, this also offers new possibilities of heat utilization for local or district heating applications by integrating these power to gas applications. So by meaning electrolysis and the methanation. Next slide, please. And in a further step, we could also think about substituting the conventional CHPs by large-scale fuel cells, as mentioned before, and therefore enable the direct usage of hydrogen for electricity and heat generation, and therefore reduce direct carbon emissions. Next slide, please. So, and last but not least, both systems, the electrolyzers and the fuel cells, could also be combined in future into a single system, for example, using reversible fuel cells, and thus allow to optimize operating hours and plant costs in a self-containing seasonal storage and regeneration system. Next slide, please. So to shortly sum up the options for direct integration of power-to-gas applications in heating grids, low-temperature electrolyzers such as PEM and alkaline cells provide waste heat potentials of about 10 to 25% of the nominal capacity for mainly spatially close applications. Downstream synthesis processes like methanation provide additional sources for heat integration, usually at elevated temperature levels. High temperature electrolyzers operate at temperatures of 500 to 1000 degrees. However, their function as a heat source or drain is depending on the actual mode of operation. And last but not least, fuel cells can and partially are already used for micro CHP applications for decentralized electricity and heat supply. And taking this further, can in future, as large-scale applications, also substitute conventional CHP plants in hydrogen or CNG-based energy systems. So in conclusion, there are quite some aspects of sector coupling that should definitely be considered and investigated for future integration of hydrogen and power-to-gas energy systems. So that's all from my side, and thanks for your attention.
Okay, thanks a lot, Dan, for that quite new insight into this area of sector coupling. Does someone has a direct question already to Hans from the group, from the audience? Yes, I see already Dietrich raising his hands, please.
Yeah, Hans, I have a question. You mentioned in the last slide some different technologies with temperature ranges. At least in district heating, we are trying to come down in temperatures. But I don't know if you have followed the morning and the sector a little bit. So at least the first temperature level, 60 to 80 degrees, is somehow in the range what we are thinking about, but definitely not 500 to 1000 for waste heat utilization. I think these high temperatures should be used also for other processes, not for district heating.
Yes, this, as I already mentioned before, these high temperature electrolyzers will mainly be an application for industrial processes because they are mainly used in a mode where they utilize heat themselves rather than producing heat just to raise their electric efficiency. So this will mainly be something for industrial applications, but I think this could lead to some problems in future. As I mentioned, this can lead to the case that industries that are suppliers to district heating grids will use their waste heat in future to operate their hydrogen production.
Okay.
And so there could arise additional heat demand for district heating in future.
Thank you.
What is actually not necessarily a problem, but maybe a new business model for district heating operator.
Sure.
We have another question from Janibek Orotsaliev.
Yeah, thank you. Janibek Orotsaliev from Kassel University. Thanks for the presentation. I have some questions about the way of how to use hydrogen. So assuming that we have a lot of electricity and you have electrolysis, so you produce electricity, and I mean, maybe you can go one slide before, so with this produced hydrogen, you can use it somehow directly or feed it in gas grids and so on. So, but what is the purpose of, or what is the advantage of using this hydrogen to produce methane again? No? So this step with methanation. So what is actually the advantage of this step? And how
yes,
realistic
for sure.
It is?
The main pathway or the preferred pathway should be the direct utilization of hydrogen, but methanation is somehow a bridging technology to further use existing gas infrastructure to minimize investments in this infrastructure in the midterm. In the long term, for sure, the direct utilization of hydrogen should be the preferred pathway.
Okay, thanks.
I had a similar comment a bit that the gas grid you're mentioning, you could actually also have the direct H2 utilization without the gas grid actually. So just closing that arrow and avoiding the gas grid in between, that might be also a way because I'm personally not so sure if the gas grid we need in the extent we currently have, since a lot of it is required to supply to end users. And if you want to supply the
yes, this is more or less something where the seasonal shifting of demand and production comes into account. So the gas grid is somehow used as a storage option.
Okay, I see that. Okay, are there any other questions? Oh, I just saw another one. Johan van Bijl from Vito.
Yes, hello, good afternoon. Thank you for the presentation. I hear also that hydrogen can also be used in industrial processes, there where you need the high temperatures, where there are not that much options to further use renewable sources. In your last slide, you mentioned also that you can use also micro fuel cells. The question is, in fact, is there enough hydrogen to use also this micro CHP in the houses? Because part of the hydrogen will be also used in industrial processes to go to these higher temperatures. And then, the question is there enough hydrogen in that case also to provide the small or the medium-sized CHP in the houses?
Yes, that's actually a good question. I think, yes, primarily we will need hydrogen for industrial applications where a switch to renewables is not really possible in other ways, such as steelmaking processes. I think if we can extend district heating this far as we don't need decentralized utilization of hydrogen in micro CHPs, this would be the preferred way.
Yeah.
Okay.
Thank you.
Thanks. Are there any other questions to Bernd or maybe also the other speakers?
Maybe a short comment from my side, Bernd again, from the Stadtwerke München. In my point of view, it's a very nice presentation and a very hot topic, because I think it's much better to use excess electrical energy to produce hydrogen instead of redispatching it or just losing it. Like the presentation before in Denmark, where we had 60% excess energy or 130% excess energy. What do we do with that energy? And hydrogen is a perfect long-term storage for that excess energy. Just a comment from my side. I really enjoyed the presentation on that.
Okay, wonderful. Good to see. I agree, definitely. Excess electricity, as long as you cannot dump it into power to heat, we use it in a heat pump. Hydrogen might be a good idea, for sure, definitely. Any other questions or comments? Yes, Dietrich.
Yeah, maybe a question about efficiency. So how much energy we are going to lose by transferring it to, for example, from the electrical grid to H2 to hydrogen first?
Yes, I actually had a slide with electrolysis efficiencies. So low temperature electrolysis is in the efficiency range of about 60%. So we will lose quite a lot of energy that way. So the preferred way will still be electrification or direct usage of electricity wherever possible. That's for sure.
Yeah, okay, that's also my main conclusion. That means in terms of mobility, not trying to come with hydrogen cars on the market, more use it in batteries, right?
Sure. So for individual traffic, electric vehicles will still be the preferred way, yes.
Okay, for heavy transport, of course, it's changing, sure.
Sure.
Okay, I mean, the role of hydrogen in the future, I guess that's, as Bernd said, and others, it's a hot topic, so how much hydrogen we're going to have, but I think we can all agree on that if we introduce hydrogen, we, in my point of view, need very much the things what you're drawing here, so especially that orange arrow that uses the waste heat, and as one of my main conclusions as well is to, if you design or plan the electrolyzer plants, you need to consider the distance to the nearest district heating network or nearest electricity heat demand or heat consumer. But we have another question. Ian Spencer.
Good afternoon. Great presentation. It's just the reversible fuel cells. Is that technology tried and tested now? Is that available on the market? And if it is, do you have any information about it?
No, not really. It's still on rather low TRL level at about 3 to 4. So this is more a long-term solution.
Right, okay, thanks.
Okay, thank you. I would like to have a question maybe to all participants. Thanks again for the presentation. The general question and answer session I would like to open for all participants, since what we've seen now is a couple of technology options. What Otge was presenting nicely, these different ways of looking at using the waste heat in different types of energy systems, planning networks, considering different heat sources, and now the waste heat. That's quite a lot of different aspects. My question now basically is, how are we going to plan our and operate our future energy systems, since all these solutions we have are basically particular individual solutions, or let's say are sector specific solutions. None of these are really considering the other one. So like the tool, like I believe there's at the moment no way to really plan electrolysis nearby waste district heating networks and take the waste heat as a source, nor is there a solution for fourth generation or fifth generation network taking the waste heat from electrolysis processes, although that's, I guess, a quite straightforward point. But the question now is, what do you think? What kind of software, what kind of methodologies should be developed or is required, or do we maybe already have all these bits and pieces for planning and operating future district heating systems? What would be your opinion here? How can we consider waste heat from electrolysis processes? How we can at the same time consider the spatial distribution of heat demand and supply and the different temperature levels and technologies for sector coupling? Is there one software we need, or is the software we have already sufficient?
We have softwares that, because what is needed when you look from a district heating point of view, that is load shifting. If you have incoming a lot of energy, then you can do it either by load shifting the demand, or you can apply the thermal storages. So we have certainly the thermal storages and the software for load shifting in building. We have it available, but it's not widely used. So from technology perspective, we can certainly do more, but we also have a lot.
Okay. Yeah, I agree. Any other comments here, impressions? From Comsoft, maybe, Josef? Do you have waste electrolyzer as a future heat source integrated in your software already?
Yeah, we can integrate as a heat source with the temperature, and we already have working on thermal energy storages to integrate different levels of thermal energy storages, like centralized storages and distributed storages. We are already working on that. So yeah, I think the technology has is that the technologies are available, but it's not widely used.
Mm-hmm. Maybe one final point, what I'm a bit missing in all that presentations is that electricity network. I mean, we talked about electricity prices, a lot about the availability of electricity, the markets, but one point that is maybe a bit or not very much considered is constraints in the electricity network. There might be a situation where you cannot transport sufficient amount of electricity from renewables away from the source. So, for example, having a wind park that is connected to a weak electricity network, and you cannot remove that electricity with the given network capacities. And that might be an opportunity that is still a bit under-evaluated, and I don't think it is really considered at the moment in the current tool settings, and this business model is basically not really considered in the current developments. I don't know if you have any reflection on this point. Otherwise, oh yeah, there is one. Daniel, please, you have a question.
Yeah, hello, Ralf. Daniel from Best Austria. There's at least in the electricity market, as far as I've seen it, I'm not an expert on it in any way, but of course there's this dispatch 2.0 or redispatch where they really try to improve the current market structure in such a way that localization also takes a part in it, because at the moment you just sell your energy somewhere on the electricity market, and nobody really cares where the electricity actually is coming from. And then in a second step, after everyone has bought and sold the electricity, the poor transition providers must find out the way of getting the electricity from A to B, and if it's not working, they have to redispatch it, and there's lots of money going into this. And I think this is one of the main points that I'm a little bit worried about. It's everybody's talking about this excess electricity that we have, And of course, this was only for a few days last year, and it's by no means a general thing we have now, that we have more electricity from renewables than we actually need. I think this is really a special case back then with a lot of wind and of course, I think it was a weekend, right? So perhaps not so much usage, not so much demand. And everybody's now thinking about this excess electricity and how we can use it, but nobody really knows how this will affect the price, because at the moment electricity is much too cheap in my mind. And this electricity, this excess electricity, once everybody thinks this is a market segment that you can use to store it in H2, to store it in the heating network, if we suddenly provide all of this flexibility, because we think that this electricity is more or less for free, then it won't be for free anymore, because there will be much more demand. So this dynamics of the market and how this will develop, I think this is very interesting. Looking forward how this will turn out.
Very good point. Any reflection on this point, or I see also another hand raising? Well, first reflection, yeah, Otke, please.
Yeah, I showed that graph with the heat demand and the power demand. So if you make the demand non-flexible, then you ramp up the problem, because then you need to build in extra capacity. And when you have those peaks, it was a unique 24 hours, but it's quite common that you have in Denmark very high peaks of excess electricity for a couple of hours. But say, if you put all the heating demand or whatever other demand as a staple load, then you need to have even more renewable capacity, and you just exacerbate the problem. And also, as for the power grid, now I'm not an expert there, but what my colleagues, which are in the heat pump industry, are saying for Germany, then the grids for the older towns, they are not dimensioned or designed for higher demand than they actually have, and also not in the buildings. So the wires, they are not capable of using too much electricity. So it's not even necessarily option to have heat pumps located there. So there are a lot of problems in it.
Yep, very good point. These integrated optimizations indeed is missing, and I would like to highlight, I guess, those sectors with the highest flexibility and the cheapest way to transform electricity into other useful heats, either hydrogen or heat, will have on this electricity. The future electricity market will be for sure have a competition here, and those sources with the cheapest flexibility and transformation capacity will win, maybe. But this is a guess. Let's go to the other question. Asad Ashfaq.
Yeah. Hi. I'm regarding your comment. I would add to it. Like, I'm working on Greater Manchester, looking at how in future scenarios we are net zero pathways we are developing. So I'm looking at how we can decarbonize the energy networks and how it will impact your electrical grid system. So, but we are working with UK, we are working with National Grid and everything. But then the biggest concern we are having is, what if we are so much depending on hydrogen? So what happens in future we don't get that much amount of hydrogen? So this is an area which there's also a question like what people are thinking about here. So that's also an addition and a question as well, comment and a question. So yeah.
Yep. Very good point. So this overall system view, how much power to heat, how much power to gas you're going to have, where we're going to place the electrolyzers, where we're going to place the power to heat, where we're going to place even the wind turbines. Nowadays, you look at a wind turbine from an electricity generation and electricity network point of view, and maybe you try to avoid that people are complaining too much on the wind turbine, that the people living nearby. But maybe in the future you need to think about dumping the excess wind in a district heating network, or using it directly at the location in an electrolyzer for producing hydrogen, and then maybe using hydrogen directly in a nearby industry, or making a hydrogen recharging station for trucks, for example. And but the question how much hydrogen we're going to have depends a bit. What are the competing options like power to heat for excess electricity, and how is the market going to be developed? That's an interesting discussion. And another one, Ian Spencer again, please join that discussion.
All right, good afternoon. We keep talking about excess power, but I was at a conference last year when we could all go outside, and they were talking about conversion of trucks from diesel to gas by 2030. We're talking about converting cars into electric. So we keep talking about excessive energy, but actually, have we got excessive energy? We're going to replace all the diesel and petrol, what's fueling the vehicles, what fly around the roads. Is anybody looking at the global picture of how that all works together? Because if I'm looking at it, if you're thinking you've got a couple of days extra excessive electricity, it's not going to compensate for all the trucks and the cars that are on the road. So I'd say we've got a shortfall of energy, and at the moment everybody's going towards the fuel cells to heat buildings, electricity to cook. So by the time we add all the cars on there and then find out our networks aren't good enough to deliver all this electricity we need, the gas has already gone because the trucks are going to be using it to travel around the country. So we're going to have a real big shortage of energy.
That's a really good point. So a massive increase of wind and PV for sure we need, and I agree with you that is not really visible in the current strategies to have so much electricity and wind or PV and hydro and other renewables upcoming. But I agree on this one. Any other reflection maybe on that comment? No, but actually it's 5:04 already. Unfortunately, that discussion was very interesting and very happy to have so much active contributions. But I'm afraid we have to close now, although the last point is missing the group photo as we had in the last section, but would like to have another one since there might be new people joining compared to this last session. So please turn on your webcam. I will try to cover as many people as possible in the screen. Why I cannot? Okay. Guess I have to stop presenting. Okay. Computer's a bit slow nowadays. Wonderful. Sorry, my computer had a mistake. Now I'm gonna hopefully soon be able to make the work photo. Now a lot of pictures are wonderful. Nice to see all of you. Now I'm gonna make a screenshot very soon. There are still people coming in. Wonderful. So one screenshot I'm gonna do right now. And I'm gonna do another one. So please, 1, 2, 3, smile. That looks very good. Perfect. So wonderful. 2 screenshots. That should be well. Thanks a lot for your participation. That's all from my side at the moment. was a very nice webinar. Looking forward to continue the work. And as I mentioned, the recordings will be uploaded to YouTube. I will send out the presentation files together with the photos. And we will have then the opportunity to contact Dietrich or me if you have any other questions, or to contact the other persons. We can also contact us, and then we can maybe forward or make the contact to the presenters if they don't have the contact details in the presentation. Dietrich, you have any other last words from your side?
No, thank you. I would like to thank everybody for joining here, and especially the presenters for the excellent presentations. I think it was a very interesting day with all our 3 blocks, with the politics, with the digitalization of district heating, and now with the hybrid energy networks. I think for sure we are going to continue a series of follow-up workshops, maybe during our next meetings. Let's see when and where. At least I think we are somehow planning to have hopefully a live workshop in Nottingham during the DHC symposium, hopefully next year, September next year. So let's see how and where we are going to meet, but for sure we are going to contact you for the next workshops. So thank you.
Yes, and any contribution from your side to both annexes, TS3 on hybrid energy networks and TS4 on digitalization of district heating and cooling networks are very welcome. Please, again, contact one of each us. And yeah, thanks for participation. Thanks for presentation also from my side. Have a nice day, and stay in touch.
Thank you.
Bye-bye. Ciao,
Thank
ciao.
you.
Thank you. Bye.
Thank you.
Right. Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye.